For the longest time, I've contemplated making a video series about building and scaling web applications. And the reason why I never did it is because I never found the most appropriate format for it. Should it be code heavy? Should it be too theoretical? Do we discuss papers? Do we discuss implementations? What's the best way to approach a topic like that? And honestly, I'm just tired of waiting, and I'm not gonna wait for the perfect format anymore. We're just going to do it. You're gonna get me on the screen. You're gonna get my iPad. I'm gonna be drawing stuff, and I'm gonna be talking about topics from my own experience, from what I've seen in the field, and from what I've explored before. We're gonna talk about a variety of different topics regarding system design and scaling web applications. In today's video, we're gonna tackle the concept of retries with exponential backoff. In future videos, we're gonna tackle other topics, but we're just gonna get started. So without further ado, let's get going. For the purposes of our conversation today, we're gonna try to keep it as simple as possible to illustrate the point. We're gonna start with 3 distinct services. Now, don't get too bothered by the size of these services. We're not really talking about microservices here or otherwise. Let's just assume that these are varying sizes, services of varying sizes. They could be micro, they could be big, doesn't really matter. And what matters here is that these are interdependent services. So in order for service A to do its job, it depends on the outcomes of service B, which depend on the outcomes of service C. Now, this is a very long data path, but again, for the sake of the argument, humor me over here. We are going to illustrate the data path by a simple example. We have our user over here who is using a client of some form. It could be a mobile device. It could be their laptop. They're using the browser to maybe use our web app. And what matters is that they are making an HTTP request that lands on service A first. Now, again, to keep this example simple, we're not going to talk about API gateways and traffic routing and all of these things. We're just going to assume that this request somehow passing through all of these different layers has landed in service A. Service A is going to make a request to serve the request to the client. It's going to make another request to service B. This could either be an HTTPS request. It could be an RPC call. It really doesn't matter. Whatever you have decided to use for service-to-service communication, it's irrelevant. And a service B to service C, again, same thing. And finally, service C is going to make either a read from the database or is going to try to write the database. But let's just assume that we have our primary over here. We're going to have a sort of primary and secondary type of setup where our writes from service C, they go to the primary, and then whenever service C wants to read data, it has to read it from one of the replicas. We're going to assume we have 3 replicas over here that are constantly receiving writes from the primary. So the way this works is with if you're using MySQL, you might be using Vitess. If you're using PostgreSQL or MS SQL Server, you have some baked-in replication solutions over there. But we're going to assume that service C only writes to the primary, which writes on the replicas to make sure that they are consistently being maintained and they stay up to date, because whenever we try to read, we want to read information that is up to date, obviously. So in order for service C to respond to service B, it has to receive some form of response from the database. If it writes, it needs to receive a confirmation for that. If it's trying to read, it needs to receive the data. Service C will then make a response to service B. Service B will make a response to service A. And finally, service A is going to respond to the client. Now, obviously, in this entire scenario, the call's latency should be in the milliseconds, obviously. If we are talking about seconds, this is a very lengthy data path. We should find ways to optimize this. We should be responding in the order of milliseconds. Now, this is the core of the example we're going to be talking about today. So let's dive a little bit deeper about when are retries needed and what could happen, what could go wrong in this setup. Now, let's assume it's Monday morning. I have been working on this feature for quite a while now, and I am introducing a change basically to service C. I wake up on Monday. it's a great new day. I run my pipeline to deploy my feature. I deploy the change to service C, which goes offline briefly, and then it goes back online. And catastrophe happens. I have a bug which totally brings down service C. Let's assume service C is being deployed on Kubernetes. The pod crashes. The service is not able to go back online. No matter how many times it's being retried, the service is just purely failing. What is happening now for all of the traffic that is continuously coming from our client? Because, you know, when you're building SaaS applications, the thing you want to avoid the most is downtime. Whenever we deploy, we don't do downtime. Whenever we deploy, the traffic that's coming in from our end users needs to continuously be served. Now, service C is down. All of the requests that are coming into service A, now they are hanging, waiting for the data from service B. Service B is trying to make calls to service C, but service C is just not available. Either service B calls are, getting hanging, they're hanging forever, because maybe we did not implement timeouts on the HTTP client that is available or that is built into service B. So this is the first layer of protections that you have to implement whenever you're doing client to server side calls or even service to service calls. The first thing you need to implement is reasonable timeouts. It's very important to have client side timeouts, which means whenever service A makes a call to service B, or service B makes a call to service C, or even service C makes a call to a database, the client that is making these calls needs to implement some reasonable period of time after which the call is going to be assumed that it's never going to be coming. And if the call does not come within that period of time, we need to return an error or deal with this in some way or another. Timeouts are the best way to handle this as a first layer of protection. How do you configure a reasonable timeout period? So is it like 5 seconds good enough? Is it 10 seconds, 30 seconds, maybe even 2 minutes? What is a reasonable timeout value? The way you would do this if you're building things at scale is you would try to measure the latency or the time it takes for service A to make a call to service B and the time it takes for service B to make a call to service C. And when you measure this time across different periods of the day, then you're going to be able to plot something like this. Let's assume we don't have timeouts and we want to configure a reasonable timeout value. If we make it too short, then our entire system is going to have more failures, more errors because of client-side timeouts. And if we make it too long, then we also risk making the system way less responsive to downtimes and problems like that. So if we measure this latency across different periods of the day, why? Because your application or your system is not being used equally throughout different periods of the day. Maybe your system is being used more in the morning than in the evening. Maybe it's being used more during the day than in the evening. So you need to be able to measure this across different periods of the day to get an accurate reading. And when you do that, you're going to be able to measure the frequency of a certain latency. So let's say in here we have in milliseconds how much time a call, how much time it takes to make a call from service A to service B, or maybe even the full path, service A to service C. And let's say here in the milliseconds, it takes, let's say 100 milliseconds. That's the first bucket. And then we have between 100 and 200. And then we have between 200 and 300, 300 to 500, let's say, and then maybe 1 second, which is basically 1000 milliseconds. So when you start measuring this, you're going to maybe receive, a number. This is the frequency. So let's say 100 calls came in between 0 and 100 milliseconds were returned. And then let's say over here we have, let's say 200 calls that came in between 100 and 200 milliseconds. And then let's say over here we have 1000 calls that came in between 200 and 300 milliseconds. And then we have another figure here and another number over here. And then when we plot the curve, we're going to see we have something that looks like this. This is a good curve to have. This represents sort of the bell curve. This is sort of a normal distribution and something that I would expect to see when we are dealing with a scenario like this one. Why? Because that means that the majority of the calls that we are making are sitting within this particular time range. So the majority of the calls are between 200 and 300 milliseconds. So what I would do in this case is I would multiply this value, let's say 250, let's take the middle, by some multiplier. Maybe I would multiply it by 10, right? And what I would also look at is the amount of tail ends I have. So how much is, what I care about most is how much is on this side over here. Why? Because I would want to look at what is the longest period of time a certain call makes. So let's assume that the longest we've observed over this entire experiment is, let's say, 2 seconds. Why do I care about the 2 seconds over here? Because if I take the 250 milliseconds over here and then I multiply that by 10, I'm gonna have a value of 2,500 milliseconds, which is equal to 2.5 seconds, right? And that means that my application is gonna, if I use this as my timeout, that is good because I'm gonna give myself an extra buffer of 500 milliseconds on top of the highest value I've seen in terms of this whole request. So I can add to myself a little buffer and make sure that my system is able to cope with some extra latency if it happens, but also not too much to make the timeout configuration useless. Okay, so we figured out the best duration for timeouts. Now what? What does that actually mean? If we implement timeouts on the level of service B, we will be able to, service B is going to be able to figure out when there's something wrong with service C. And when it does that, it's going to be able to make a determination. Do I fetch data some other way? Is there data that I can get from a cache, for example? Or do I just want to fail and then return that failure to service A? In that case, service A is able to make another determination. How do I deal with this scenario? Do I return an error to the user? Do I tell the client that we timed out and we cannot really figure it out? Maybe we just say, hey, sorry user, service is down. We're having some backend issues and we're not going to be able to serve your request right now. Try again in a few moments. Or there are better ways to deal with this, because if we always return the errors to the end user, our system might look like it's not really reliable. Because if the frequency of these issues is high, then obviously nobody wants to look at errors all day long. And then at the same time, with the complexity of the front-end applications nowadays, returning these errors might be a bit complicated, because you might, some module, for example, in your React, some React component, let's say, might be fetching data from the backend, and then that call failed. How does that component, how should that component react to this particular scenario? And what happens in the case where service C suddenly comes back online? So my failed deployment, luckily I had feature flags and I just simply turned off that feature and that brought back service C online. So how do I deal with this particular scenario? My front-end application now is in a sort of a limbo situation and doesn't really know whether the calls that it's making are succeeding or failing. It gets a bit messy. What is the second thing we need to do here? It's not only just to implement timeouts, we want to implement retries. We want our calls to be retried, or certain calls, a subset of our calls, especially the service-to-service calls, to be retried. Now, let's clean this up a little bit and let's talk about retries. So again, the HTTP request comes from the client side, goes to service A makes a call to service B makes a call to service C is down. As we implemented timeouts on the level of the services, we need to implement retries as well. So another change to our, let's say, HTTP client in this case, on the level of service A, service B, and service C, is to implement retries. How do we implement retries and what do we do here? So let's assume we have timeouts. It's very valid to try and retry requests whenever the client side times out. Why? Because a timeout is an indication that something went wrong, and maybe if we retry the call after a certain delay, we might be able to get the response. So how do we implement retries? We start with an initial delay. Obviously, you don't want to immediately retry with the most basic trivial way, which is to implement a for loop and retry 5 times. That's obviously not what we want to do, because these retries will happen very quickly, one after the other, and it's not going to give any time for service C to recover. So what we want to do is to implement an initial delay. That initial delay is just a constant. And again, just like we did with the experiment for figuring out the timeouts, we might want to do something over here, try to figure out this value from data. And if we cannot figure it out, we just use something that makes sense. So maybe we can start with a 5-second delay. And after that 5-second delay, we can make another call. So this is call number 1. Then we make another call to service C. And then we wait again for 5 seconds and we make a call to service C again. And still, if we're timing out, we're going to wait one more time. And then we need to define a maximum number of retries. So maximum retries over here, let's say it's 5. So what ends up happening is we're going to have a 5 calls maximum. And then we're going to have 5 seconds wait in between each call. So let's assume this is the wait, and this is when the call happens, right? So 5 seconds in between. Now, maybe our service C comes back and returns a response on the 3rd try. Maybe it returns it on the 2nd try. Maybe it requires 5 tries and still we don't get a response from service C. All of these are reasonable scenarios that might actually happen. So is retries gonna save the day? Fully 100%? No. But it's going to help us try to recover before we send back that error message, to the client, if we ever need to actually send it. Retries will actually try to make our services a little bit more resilient. The same retries will be implemented on the level of service A as well, and on the level of service C, maybe with the database. Now, what is the problem with this? The problem with this trivial implementation, a very simplistic implementation, is that it's not only one user who's making requests. Maybe we have 100,000 users making requests to service A. What happens in that particular case? Instead of each request being one call that goes through our system, now we're going to have 100,000 requests that are going to be retried 5 times. So you're going to have 500,000 requests within a certain period of time. That's probably going to break down the entire system even further. That's going to worsen the situation. Why? Because as soon as service C comes back online, it's going to deal with the deluge of requests. So let's assume in a normal scenario without retries, right? We have the following plot. This is time. And this is the number of requests that we have at a certain given point in time. Let's say service C was dealing with this amount of requests. It goes down to 0 because why? The service is down. It's down for a certain period of time. And then when it goes back up, it will go back to this state and it will start serving this amount of requests. However, in this scenario where we implemented retries, the chart might look as follows. Let's take another color. It will look probably something like this. It goes on offline, and when it tries to come back online, it might be serving this amount of requests instead, and the service might not be equipped to handle all of this particular load. And this value, this figure here, that just jumped from 0 to that number, could break our service and crash it all over again. So we might end up in a situation where we have something like this, and that's not something we want to see at all in any of our charts. So how do we deal with that situation? Let's come back here. We have retries. We tried the simple algorithm. Now we're going to try a more complicated implementation, and that is exponential backoffs. Now what exponential backoff is relatively simple. Let's discuss it. We're going to have the initial delay. We're going to call that IDT. That's going to be a sort of a constant of 5 seconds. Then we're going to have the retry delay. We're going to call that RDT. And that's going to be a simple formula calculated as follows. IDT plus, which is the 5 seconds, 2 to the power I. I is going to be the count of retries. Basically, if we have a for loop, you know, for I equals 0, or we might start from 1 or any other number, this is the cursor that we're going to be using. That's going to be the value of I. Now, what that means is for our initial call, it's going to fail. Then the first retry is going to be RDT0. It's going to be 5 seconds plus 2 to the power 0. That's going to be 6 seconds. So instead of retrying after 5 seconds, we're going to retry after 6 seconds. RDT1, that's going to be 5 plus 2 to the power 1. That's going to be 7 seconds. RDT2, that's going to be 5 plus 2 to the power 2, 9 seconds. RDT3, 5 plus 2 to the power 3, that's going to be 8 plus 5, 13. RDT4, it's going to be the last value we have, 5 plus 2 to the power 4, that's going to be 5 plus 16, that's going to be 21 seconds in total. So we moved from 5 in the trivial implementation, 5, 5, 5, to the following schedule. So let's actually plot this to see how it's gonna look like. Let's assume we have this y-axis, and then we have this x-axis. On the x-axis, we're gonna have I, and on the y-axis, we're gonna have r dt. So let's put some values here. 1, 2. So previously, we had a constant value of retries, 1, 2, 3, 4, 5. That's going to look like this throughout all of the iterations. And then in the second example, with the exponential backoff, we had the following. We had 0, and then we had 1, 2, 3, 4, 5, 6. That's the first value over here. So we jump from this to this. And then we have on number 2, 7. Number 3, we had 8, 9 over here. Number 4, 10, 11, 12, 13. We had this. And number 5, we have something here. So when we try to plot it, it should look like an exponential curve starting from 0. And this will, drastically delay the amount of retries. And if you look at this plot, that's how that's the shape of it, or that's the shape we are intending it for it to have. So by implementing this simple formula, we will have something like this. Now, what is the problem with this? There's still a problem. This is not the end all be all solution. And the reason for that is when we try to plot sort of the requests, and if we try to distribute them to see if the requests are still being cluttered together or clumped together, or they are being more distributed over time, we see that even with exponential backoff, the requests are still being cluttered together, especially at scale. And in order to illustrate this point, I'm going to reference a great paper from AWS that talks exactly about this. So let's jump to the second screen and let's talk about the distribution of requests within periods of time and explain what's the issue there. This paper was published by Mark Brooker on March 2015 in the AWS architecture blog. This paper is referenced a lot when talking about retries and exponential backoff. So there's nothing really fancy over here, but I want to talk about a few distinctions and explain a few concepts through this paper because it's a really good one. First of all, the formula for the sleep or for the duration in between retries is a bit different than mine, and it has some nice additions. First of all, sleep over here is basically our RDT value. And then you will notice here that they have the min function. And the min is between two values, the cap and then this value over here. Why? Because this value is basically base multiplied by 2 to the power attempt. Base is basically what we referenced as initial delay. 2 is the same number. And attempt is the exponent, which in our case was the value of I. And here they are multiplying base by 2 or multiplying the delay by 2, while in my case, I added 2 to the power I to the base or to the delay. There's no major distinction between these two. If you want the initial ramp up to be slower, you would use a summation. If you want it to be, bigger, you would use a multiplication. But it doesn't really matter. You're gonna get sort of the same outcome towards the end. But play around with these formulas and see what you get. Now, the cap, what is the min introduced for? The second parameter could grow very big. And you obviously don't want that to grow to very big numbers. You want to cap it. You want to limit how far that number can grow. So what you would want to introduce here is a minimum between the cap and the exponential value that you calculated. And you would choose the minimum value between the two, because if the exponential value is growing like to gigantic numbers, you would want to cap it at a certain maximum. And this is how you would do it. This is a great addition. And then the second thing I want to explain is this distribution over here, which is really good. On the y-axis, we have the call count, the frequency, the amount of calls that were received in a certain period of time. And then the x-axis is time. And notice here that time is in milliseconds, not in the order that we just discussed, which is seconds. Again, that was a theoretical example. This is more of a production setup. I think they were talking about a database over here. So milliseconds matter. Now, the way to look at this chart is, it took me a while to see it, but here's the ruler that will allow you to see it a bit more clearly. At every single point in time, as we move along the x-axis, there's a frequency or a number of calls that were made at that particular point in time, and you will see that by the value on the y-axis. So for close to 0, we have 1, and then a little bit higher than that, we have maybe, 3 or 4, and then we have another value and another value and another value, and it goes along the entire axis. That's how you should see it. Now, what you will observe is that there is a clustering of calls that are being made. So you would observe a cluster right here, right here, right here, right here, and yes, there is a delay between these, but there is a clustering of calls, which means that the exponential backoff is aiming to reduce the amount of calls that come together towards the service. But if we are observing clusters in our distribution of calls over time, here it's getting worse. That doesn't really solve our problem. Then the formula we have just simply distributed these calls over a longer period of time, but it clumped them together in specific buckets. So in order to solve this, they actually did something interesting, which is to add jitter. Jitter is, again, a randomization. You can add jitter in many different ways. You can add jitter by, for example, coming up with a random value between two figures, and then you could multiply that, for example, by the base, multiplied by 2 to the power attempt, or you could do what they have done here, which is to calculate a random value between 0 and their previous formula, basically. And what that does is it distributes the calls to something more like this. So over time, you will see here that the frequency of calls has been, and you will see that the calls are distributed more equally across a longer period of time, and that reduces a little bit the contention on their service because of that randomization that they just added. Yes, there will be some small clusters, but these clusters are not as big as they were before introducing jitter. Now, there are a couple of ways to introduce jitter as well, and different ways will lead to different outcomes. But again, I don't think anybody is building services at this scale. So the ways are described over here in the paper. This is another one. And this is the one this is also another way where you are adding the randomization between base and sleep multiplied by 3. So there are a couple of ways to do this, and each one will have different outcomes. But you can read this paper on your own and understand these different implementations and their impact. But at the end of the day, what matters is what works best for you and your situation and your case and your application, you will have different demands, you will have different needs, and your amount of, the distribution of calls is definitely different, because the type of work that your services will be doing is fundamentally different than what we're seeing in this particular paper. So going back to our initial drawing, again, retries plus exponential backoff is the solution over here. Obviously, not every call that it fails requires a retry. Like, for example, authorization failures do not need to be retried. 404s do not need to be retried. Any non-failure doesn't necessarily need to be retried. Okay, so don't just take this pattern and implement it blindly everywhere you go. You need to think about the scenario, what you're trying to achieve, and how you want to do it. Retries and exponential backoff is good, it's useful, but you also need to be careful not to make your situation worse with your implementation. So measure, implement, tune it, put it in production. And with that, we come to the conclusion of this video. I hope you learned something interesting today, and there will definitely be more videos in this series, and I will catch you next time.